Probably do have it.
Oh,
It's open.
are you doing?
No, just recording. Sorry. I'm not doing anymore. I'm just recording it so people can like look back at the lecture.
I'll stay out of the camera.
Oh, don't worry about block here. You can totally say, don't worry about the camera. You can sit in front of it, you don't have to block it. If you want to sit. Um.
Yeah, that's
You know, I'm gonna camera, we were practicing this lecture on camera. And when I tell you like the markers, like the markers so beautiful, like this is not. The markers are now oozing with me, it's so nice. So I was like, kind of just, we have so many pens, you said that's the department boundary. Yeah, like you're not gonna miss any, and there's so many that's like. I was like, yeah. Brian Dale let me see if I can get steal them. I was like, I want to feel this. Okay, we said we don't want to try and remove this. Can you? Later, so. Wait for 3 more minutes then. I'll talk about a little bit about today's lecture. Is this loud enough for everyone? Or should I go louder? Okay, yeah. Okay, so today we're going to be talking about case centers and LPs and translating those. It's gonna be really fun. This is actually a bit of an experimental technique. So there won't be any slides for this, however, I have notes that I might send to you guys if that would be helpful. So yeah, and the whole thing will be recorded too, and sent to you guys afterwards. But yeah. So do you guys what did you guys cover in your last lecture actually? Sorry? What did you guys cover in your last lecture? Okay, yeah.
Correlated and independent.
So today we'll also be talking about LP rounding somewhat. So I'll go over general our inputs for an LP, I guess. The ILP, the LP version, and then how to do the randomized rounding for the LP. So let's talk a little bit about our input. So our input, we're gonna have a set of points P. Will be a set of points P. A distance matrix. And this is gonna be really similar to, do you guys remember when you guys did the P set? This is gonna be really similar to that distance matrix you got, you guys did at Gonzalez, for your P set, you guys remember how that looked. So these are gonna be I can clarify this. These are gonna be metric distances. And then we're gonna have a which is the number of centers that we want, the case can be an integer. Then this is gonna be the trickiest part to recognize about, okay? So bear in mind that work with me here. It's gonna be called sum, min, d, and don't worry if you don't get it just now, I'll go over it. D being that it's greater than xij, EI, EJ, for all, EI, EJ is. And you might be looking at this like, what on earth is this? And, what we're doing today is gonna be a little bit different than what we've been doing before for LPs. We're not working with objective functions. I'll talk a little bit about what that means later. But, basically, we have some minimum Z that is going to represent our R. And for LPs, you can't really, we don't know what our R is, and you can't really like guarantee an R. But we're gonna show later how, eventually we calculate our R in a second. But basically, we're guesstimating the R, if that makes sense. We don't know what our R is. We can't guarantee, that our points are going to be like perfectly R. So we're going to guess the best value, and that's going to be represented C. So we're basically saying that, every single point, is going to be within R of its assigned center. But we don't know what R is, right? R is going to be represented with this minimum Z. So we're basically saying that every point that's assigned to the center must be within R. So, I'll get to what I mean in a second. Let's talk about the goal first. We're really big enough for everyone? Okay, awesome. So our goal is to find a set of points, find a set of points. Sorry, not set, so a set of centers. Centers. S. What size should we make it? Yeah, the centers of size K. Such that the maximum distance between any point and its center K. Well, I won't say it's, let's say it's near a center. Minimize. So we're finding the maximum distance between any point and its near center, and we want to minimize that. So we're minimizing the maximum, min-max. Everyone following the verb? Okay, so what do we mean by finding some R? You don't even know what R is, right? Isn't that kind of crazy? And I'm gonna actually write on this board. So basically, we have to guess optimal radius R. Suppose we try all possible R's. At some point, you're gonna find that optimal R. You try every single possible R. So do you guys get what I mean? If we keep running this and we keep trying every single possible value, R, which is the distance between the points, we're gonna find some possible R. We're gonna find the optimal. So let's just assume when we do our LP, that we have the optimal radius R. So therefore, any solution that fits the constraints or satisfies the constraint is the solution for K factors. with radius at most R3. Okay, so we're trying every single point. Yes, and let's do where's the point? Any, sorry, not any. I'll repeat this to you. So you're guessing that point is R way. And basically we're trying every single possible R. How many times are we going to be looking for that number R? What is the runtime? So can everyone see? You can't see you with this like going out here. No. Would it be all the set of here? We're getting there. So obviously there's a lot of the distances between all the sections. What is the runtime? Yes. Well, we're comparing two sections and then we're running it. So think, let's say that it takes like. So it's basically n choose two actually. No, we're gonna run this n choose two then. We're gonna choose, find the possible distances with every single circle and choose two, which we can upper bound by. Oh, that's good. Yes. We have a distance matrix that is. Well. It's not the lookup, that's the hardest part. It's finding the optimal part. So we're running this like. LP, n squared. For each possible. Distance. Which would represent NP in our input graph. So what are we using? Use the distance matrix, I guess to find these numbers. Distance would be here. But our Z here is some radius. We don't know what the radius is. So we have to do that computation here. N squared times until we find our optimal radius. Does that make sense at all? Okay. Yes.
Sorry, what computation are you doing?
Oh, yeah, so this is just for this step. So basically, when we run our LP, again, we don't know what our radius is, right? So we have to basically keep running it until we find some radius that satisfies our basic constraints. So it's kind of just like you're trying to run through every single possible radius, essentially.
And this is like the radius between, I don't point and maximum.
Yeah.
And it's like inside the maximum distance from our center.
Yeah, because we can't just tell the LP. It's technically like that one, just tell the LP to, I guess, min max. Those are Brian's words, not mine. So you can ask for those applications. But because it's like, not recommended, that's why we have to do this stuff where we guess the radius. Is anyone like that confused?
Why are the values that we end up guessing all going to be the same? In the are they going to be different in that one? Or are they going to be the same? And then we're finding the value different.
Sorry, what do you mean by that?
Like in the distance matrix, we'll have every possible raise will point to another. So in the one we get will just be they'll be the same.
Yes, we'll do the same. And then we'll have to run that for each time, for each, I guess, distance. We'll have to try that in our LP, and we're gonna do that over and square that. This over and square value in that distance. That can make sense to you about? Okay, let's get a LP then. Sure. So like I just said, when we do the ILP, we don't have an objective function, and you guys have probably never seen that before for an LP. So do you guys remember in a objective function that you guys did before in class, would be something like, you would probably presume that it'd be something like, oh, find the min, max, blah, 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 right? You guys remember doing that in the LPs before? We're not doing that this time because case center works a little bit different. and it's just bad when you use it. So we're gonna go with no objective function. Wow, shocking. So no objective function. And now we're going to say, let's define the decision variables actually. So let yj be a decision variable. And let it be one if pj is a center. And then we're gonna do let xij be another decision variable, I guess. So it's gonna be one if point I is assigned to point j. Zero other places. And I'm gonna clarify right here that a point can be assigned to itself. So when I'm saying Pi and Pj, these are points in the same cluster. These are the exact same points in P. Pi and Pj can be the same point. And xij, it's possible. So if you're looking at like some point x, right? Some point that's not a good variable. Let's say some point like point L. Point L can be an xPi and it can be a Pj. Points can be assigned to themselves. So is anyone confused so far by the decision variable? Yj is again a decision variable. One if Pj is a center and zero otherwise. And that's important. Why is this important? Tell Yj. Anyone? Why do you think we want to keep keeping track of which point is it? Yes. Well, of course, we, I guess we just want to keep track of which points are centered because that's how we find out if they're centered or not, right? That's how we do our like, LP and fill in our xij and do our algorithm. So we need to keep track of which points we assign centers so that we can differentiate them between points that are not centered. Again, xij, just check if a point is assigned to a center. Okay, so again, there's no objective function. No objective function. And such that the sum of each point j and p, yj is less than k. What does this do? Can anyone tell me? Yeah, so like, where did I do that? Oh, yeah, okay, yeah, so this just basically means that num of points chosen in S is less than K, which is our number of centers. That makes sense, right? Less than or equal to. Okay, next step, we're also going to say that the sum of EJ in P xij is greater than or equal to 1 for all point I in P. What does this do? If we know that the decision variable xij is 1 if a point is assigned to a set of j. For every point j. For all point I in P, all xij's are greater than or equal to, and, yes. Yes, okay, everyone see this? I don't want to be watching this too. So basically, it just makes sure that every point is inside the center. And of course, again, PI's and PJ's are the same set of points. So centers are just assigned to themselves. Is that gonna make sense? Awesome. All right, next step. Xij is less than y, less than or equal to yj for all pi, pj in P. Such that. Wait, no. Okay. Can anyone tell me why I would do this? Think. Yes, Miranda.
It's like if J is not essential. But R J is zero, then X I J must be zero.
Yeah, so this basically ensures that a point has to be assigned to children's center. Okay, here comes the trickiest part. This is gonna be a little bit tricky. It's gonna be xij equals to 0 for all pi, pj in P, such that the distance of pi, pj is less than r, which is RC. So what does this do? Xij equals to 0 for all pi, pj in P, such that the distance pi, pj is greater than r. So again, R is the Z that we manually input, we're guessing R. So we're putting in this R. What does this R do? Yes, what's your name? Yes.
So if distance between 2 points is bigger than our optimal R, then we don't assign.
Yes, exactly. So we want to make sure that every single point that's assigned to a center is assigned to a center that's within our distance. Does that make sense to everyone? So you can see how, like, if we have this, like, we choose this really tiny R, what's gonna happen if we have this constraint? Are all points going to be able to? Yeah, not all points are gonna be able to find a center, right? Because this will be invalid. There's no possible solution if the R is really tiny. Then we can't satisfy this. So then the LP would, ILP, yes.
So then what do we get? Do we have any order? Do we like start with the biggest and then keep going until we get something that is like too small with it?
I don't know the exact answer to that, but I think you're right, because we'll just go from the smallest value up until we get something that actually satisfies every single constraint. That can make sense. So again, this is an ILP, cases are ILP. I'll look at that actually. This is an ILP. And it's only going to solve if it's possible to fit every single constraint. So if it's going to be able to satisfy every single constraint in here, it's going to return something. Otherwise, it will not return. So by having the C that we define, and we calculate through that, basically, we can guarantee that we'll be able to see if we can find our optimal radius power. Does that make sense to everyone? Did I cross your hand? Yes.
Just a clarification for the definition B, those like the X is being multiplied by the distance.
What?
So the X is being multiplied by the distance in definition. Like it's X like a time.
Oh, yeah,
Okay.
because again, what is xij?
Xij is whether a point is time.
So what is its value going to be? Okay, 0, 1 or 0, exactly. It's either 0 or it's, yeah. And so what does that do if it's 0 or 1?
Essentially, if it's 0, then it says that the distance doesn't matter.
Exactly. Does that everyone get that? Ellen, think about it? That's fine. Okay. But yeah, exactly what Annabelle said. It's gonna be zero if it's not assigned. Did that make sense? That point. So we're only checking the distances between all PAs and PJs that are assigned to each other. Everyone got that? Okay, here comes the ILP part. Wow, very cool. So YJ is gonna be in the set of 0, 1. XIJ is gonna be in the set of 0 or 1. These are for all P, J, P, for all G. Okay, does everyone understand this ILB-ish? Any questions about how we're doing this? Distance must be between them R for all points. Okay, let's translate this into an LP. Do you guys remember what you guys said, learned in class about ILPs and LPs? Every single ILP can be translated into an equivalent LP. Everyone got that? Okay, so let's translate this into an LP. We're going to be basically doing the exact same thing for the blacks and the LP. So, let's just start with the relevant. No convective function. Such that the sum of J and P, Y, J, and K, sum of J and P, X, I, J, one, I, and P, X, I, J, blah, blah, blah. And P, X, I, J, equals to 0. Okay, so it can be the exact same thing for the constraints. What separates an LP and an LP? This was really yes, I don't know. Oh, I'm sorry, what's your name?
Sydney,
Sydney? Yeah, Sydney. What separates an LP and an LP?
that like YJ and XIJ don't have to be just 0 or 1, so they can be within their range.
Yes. Sorry, what is that for next?
No.
So we're gonna have this for YJ. For all PI. P 0 XIJ for all PI. You guys have a moment to copy that down. Does that make sense? To everyone? Yes. Oh, sorry, that's a dash, not a negative.
Oh,
My bad.
makes sense.
Good question though, thanks for, so this is an ILP. This is LP. Cool. Yes, there's not. Yes, you are right. When I took these notes, we did not have, your, oh, no, yeah, it's a greater sign. Why is it greater and why is it not greater in? Degrees greater as well. Anyone else want to do personnel, and why is this a greater than and not a greater than? I know you want to do it now. Anyone else? Tune in? I don't know. All right, Annabelle, do you want to?
Yeah, so since we're assuming optimal gradients are, then if I is assigned to Jen, grades, etc., then it has to, their distance has to be less than.
Less than or equal to, exactly. Thank you, Annabelle. Sorry, we'll call you. Just- Your eyes look very confident. To answer, so. Yeah, the second exam personal, it has to be less than or equal to 3 years. I think true, but this is, this basically says that we're gonna set to 0 if it's greater than the radius. So we can, it's gonna be greater. So if it's greater than, we'll basically say, no, we will not assign you. You get 0. Yes.
So what about the two experiment? Like, are we gonna see something that makes it experiment?
Well, the experimental, I guess, is no objective function. This is not like an actual algorithm. This is, apparently Brian defined this as a myth among the algorithm community.
So it doesn't work.
Well, it works. It's just not like a defined LP translation, but it's a very mythical. Yeah, you guys are watching this type of legend. How cool is that? Yeah, isn't this kind of cool that you can do this? That we can translate case center like this with this magical definition here. With no objective function too. Wow, so cool. All right, let's talk about the LP rounding algorithm. It's really complicated, I have to write on that. Alas, so the way so. All right, so let's talk about LP rounding, and we might even finish early. Get all of that. Yeah.
I'm sorry, what do you say that maybe objective function, the objective function usually like minimize or maximize?
Yeah.
Right, so then why can't we make the objective? Like, minimize?
Yeah, so, that's a great question, and I think a way that some people. You could, I think, propose like this idea, min, max, PI, and.
Oh, we're saying that five.
Yeah. This is really bad for me. Brian is not like it. So Brian is like, this, we hate it so much. No objective function. We will use this constraint instead. So much sexier, so much cleaner. Wow. Yes. Any other questions about this? Okay. Let's talk about rounding then. So the idea that we want to have when we round, we're basically let P be unassigned and P being the set of points. So, P be assigned, P referring to set of points. For 1. Okay. So for each, 1 all the way to the number of centers. Choose any unmarked point. P, J, and P. So while Yj less than 1. And why can Yj be less than 1? Which one of these happening like on that map right now? And well,
That's like, it's not. Or are you saying like why in terms of like the L?
LP,
Oh,
this is
yeah.
LP rounding.
Because it doesn't have to be an integer.
Exactly.
It can be like,
So again, in our LP, we define Yj as any value that's in between 0 and 1. So Yj, we can assign like these integer values to like maybe every single point that's greater than 0. Yes.
What is unmarked function?
Yeah, so sorry, I didn't explain that. But basically we have a unassigned group of points. We haven't marked any of them yet. So this is one of those, like it's nice, crisp, clean. And they have these like beautiful values that come from, right? So cool. So cool, so much. Yeah. So while this is our LP rounding, so what we're trying to do here is we're trying to basically find our centers. And we're gonna approach it through a really unorthodox way of running. So while YJ is one, we'll find closest unmarked J prime. So we're looking at some point PJ, we'll find the closest unmarked prime PJ prime. And then what we're gonna be doing is we're gonna be stealing this value. So the value of YJ is going to be basically equal to the value of YJ plus the value of YJ prime. And then of course YJ prime is equal to 0. So this value got stolen. How's that? Okay. Then for every point with xij prime that's greater than 0, xij is going to be equal to 1, xij prime is equal to 0 for all double primes such that xij prime double prime is 0 for all. And so what this line basically does is it says, if you have, and so every point that has an xij prime that's greater than 0, 1, this is now going to be assigned, this I is going to be assigned to the PJ. And if it's, this I is assigned to any other point j prime, then it's not 5. Then we're gonna call
Is it the xij prime of the one or just xij?
this one? Yeah, j, because you're gonna set every single point that's not j equal to 0 for all every single I with x or j prime greater than 0. So we'll go over this. So I know it's a lot of information. But we will go over this in a second. Then we're going to call PJ marked, and then finally, when we're done with this for we're going to call PJ marked. So I'm gonna throw a lot of information at you whenever this time. We can go over this one more time, and then I will run it on our graph. Sound good? So, basically, we have this unassigned set of points. For, the 1 to 10, this is all of them, are done. All in 4 of those. So while we still haven't found a number of centers, we're gonna find any random point. Some unmarked point, each. Let's call it this is our unmarked point. We chose it. While this value is less than 1, we're going to find the closest unmarked point. We're going to steal its value. We're going to set that point's value to 0. And then we're going to change the xij such that all the things that were assigned to it are now going to be set to 0. And let me just draw it one for you on the graph. Visualize this a little bit better. So yeah, maybe just a little bit. Okay, so all the green stuff that we see here, this is going to represent our xij. And all the black stuff you see here is going to represent our yj. Right, comes. So our YJs are the points that they've been assigned to the LP, basically all of it. And all these green arrows that you see here are the points that are assigned at XIJ. So as you can see, this YJ that we chose here, this point, let's call this point P. Point P assigns 0.5 to itself, but it also assigns 0.25 to this random, and it assigns 0.1 to this point. So that means that our LP has assigned this XIJ, this being the I, this being the J, that's 0.25. This XIJ, this being the I, this being the J, that's 0.1. And this XIJ, this point being itself, and the J being itself, that's 0.5. And the Y J that it sends is on a phone, 0.5. Does that kind of make sense? Is anyone confused by this graph? Yes.
I'm confused. Can we go over the formulas? I'm just trying to follow, like,
Yeah, yes, Brenda.
could you clarify the information of the two calls at the bottom?
Yeah, Brenda, these are for. This should be in this one. Just one of them. Let me see how much is in it. My bad. Okay, so this is one for this, right?
For loop inside the while loop? Is the for loop inside the while loop?
Yes, it is.
Okay, that's the second one.
Look at this. So for I and K, we're choose the point, then we'll do this one week, and this will be inside here. Yes. That's it. Anyone confused by the indentation?
Sorry, so for loop is inside the while?
Yes. But this call BJ is outside the flow, it's in the wild. Yes.
Are YJ prime and PJ prime different things?
Yes.
Okay. Where did YJ prime come from?
Here. It's. There are different things, but YJ represents TJ. It's a decision variable. So PJ is the point itself, YJ is the decision variable representing the setup. So that's PJ prime. PJ point prime is very just the random, some unmarked point. So this is some point P, this is some point PJ prime. PJ prime. And again, don't forget what XJ and XIJ and YJ are. The decision variables that represent if a point J is a center, 0 otherwise. XIJ is if point 1, if I is assigned to J, 0 otherwise. So our LP again is going to find some value between 0 and 1. And so therefore, over here, when we say YJ prime is equal to 0, we're saying that it's therefore it's not a center. It can't be a center. We stole this value. So why don't we see how this works, I guess, in terms of like, let's run this algorithm through a little bit. Okay, so the first thing that's going to happen, we chose this query, right? Let's actually not work. Okay, so for 1 and K, we'll choose some unmarked point J and B. All right, we chose it. While YJ is less than 1, is this less than 1? Awesome. Let's find the closest unmarked PJ. This is our closest unmarked PJ. Okay, so now we're going to steal its value. How do we steal its value? We're like, haha, your value is mine. So then it's going to be 0 now. Is that going to make sense to everyone? Still its value, 0, it's so bad. Yeah, so now for every single point where XIJ prime is less than greater than 0, So we're gonna see that every single point that used to be assigned to J prime is now gonna be assigned to J. Just go all the points ahead too. So this will be here, and this will be one. Just slow it. This will be 0. This is not gonna be assigned here. 1. Does that make sense? You look confused, one.
About the last two things, the last two things.
Yeah, so these again are not the y they're the xij's. And what are again are the xij's? Xij's are the variables that are 1 if a point is assigned to another point, 0 other point. So basically for every single point that used to be somewhat assigned to this point, they're now going to be equal to 1 and they're going to be pointing to here. Does that make sense? You just solved the silence, so that's the fun. Yeah, okay. So we finished that. Is this 1 yet? No, so let's go at the next closest unmarked point. Hey, look, this one looks pretty unmarked to me. Let's steal the solid too. 0. 0.85. Okay, so we just stole that point. Does that kind of make sense how we stole it? And what's your question?
Sorry, going back a little bit, what was the xij double?
Yeah, so, it basically says that if any point,
I only think those x connected points to it, and it would be.
yeah, so you see how these are pointing towards us? What does that mean? These are the eyes, that's the shape.
So saying if those were also j's and there were points like that.
No, we're saying for every single eye that used to be pointing to this one shape. This eye is not pointing to this shape.
Yeah, what about like the j double?
Yeah, so this is J prime. So for each J double prime, that used to be pointing to J prime, it is that double prime J is now pointing to J. Because the I is the same, this is I. So for every point with xij prime greater than 0, what does that mean? J prime is this, you know this is J prime. These are I's, because again, you see these arrows, the existence of these arrows implies that the xij value is greater than 0. So what we're going to do is we're going to do steal as a sign.
What is the j double prime?
Some point that's not J prime. So this is J. This is J prime, and drawing that down. Yeah. Or J. What J? It's going to be some random arbitrary point, J double prime. Maybe this is also a J. But we're going to represent them under the umbrella. So point that's not the point that we're looking at. Everything is still. So remember, we stole the point center assignment.
I thought this j meant that something was. Oh,
PJ is the point itself. YJ is the position where it's assigned to the center itself.
but the xij means, like, I thought that those things would be written on the I value and the j part would be the center of it.
Let's break it down a little bit, okay? So let me just go to this board. So we have the point itself, the point I or point J, and they're gonna exist in P, okay? Everyone following? Then we have the position variable, YJ. So it's going to be 0 if not center. 1 if center. Then we have our decision variable xij, and it's going to be looking at 2 points, or maybe they're the same point. Point I, point J, and it's going to be pointing to J and saying, hey, that's my center. If it's this value is 1. Otherwise, it's going to be 0. Who are you? Does that kind of make sense, Annabelle? Yeah. So P and PJ are the points themselves. Oh, sorry, any questions?
No, I was just trying to.
Okay. Sorry, were you saying about?
So then, like, what is the double part of it? That's there.
Yeah, so again, this is just J, this is J prime, we're using this to represent like the center assignment that we stole. So this used to be a center, right? It had some values, some points that were like, hey, we're gonna assign values. You can be our center for now. We have like, we assign a point, maybe 0.1 towards the credibility of your center.
No, what is that I? The I is like, this is the X I means this is like the P day prime and P day, right? No, that's like.
So let's talk about this a little bit. Yeah, so I'm just gonna confused. So you see how this used to assign 0.1 to here? That means that this used to be an I and this used to be a chain. So X, this is, let's call these A, B, C, okay? A, B, C. So let's instead of saying I and J. So before X, A, B equals what? What was X, A, B equal? So that kind of makes sense in your head. Okay, now, when we're looking at this, we're saying so we're again, while Yj is less than 1, we find some unmarked PJ. That's our point here, PJ prime. Then we're going to look at every single X value that has J prime. So this we don't know. We're gonna look for every single point that's gonna assign to J prime.
Sorry, wait, and like.
Yeah.
Do you think it's that eight?
Yeah, but we want to follow this algorithm here, right?
I guess I'm confused to there's something I don't know, like which one's somewhere, like an X I day is equal to 1 means that the, like, is the same thing as.
Yeah,
It's like A, B,
that's the, okay. Why don't we label all this? Why don't we label all this? Okay. So basically, we choose point A. Yeah, let's use the ABCD example. We find some unmarked point, that's gonna be A. We look for the closest unmarked point, that's B. So then we're gonna steal the center element. So then y of A is going to be YA plus YB. YB is bound to be equal to 0. All right, so now for every single point for X blank B, which was J prime. Now that I, so for every single I in here, so 4, I, and does this kind of make sense to you guys? Every single point that should be assigned to B. Let's call this point everything in that whole. Then X point A is now going to be equal to 1 because we're stealing B's center. Does that make sense? Yeah. So again, we see here, okay, so maybe this point here, it used to be pointing to something else too, some random way over here, and let's call this. So let's call this C. So X point A, so looking at X C A equals 1, okay? Now we're gonna take this same C, we're gonna move it down. We're gonna check if we're gonna check if D is also looking at other points of center. We say we can't have that because now we're going to have D point to A, XDA is going to be equal to 1, so therefore maybe XDA has to be equal to 0. This B can't be allowed to point to this no longer exists. It can be 0. Does that make sense to you?
Is that even double one?
Yes.
So then in the previous example, we didn't have. Or yeah, like the J double one, is that?
Yeah.
So then like the previous example I was asking, like what is data when time to get what? Like before you added.
Yeah, sorry, I guess this would have counted, but yeah.
Like, oh, that's right.
Well, because this used to be a time here, right? The X, D, B was a thing, but now it's zero. So basically, every single thing that has, the same thing goes with the X, D, B.
What makes that something? I like that. Some other point.
It's gonna be some, it's just like a very whatever percentage thing. But then, okay, I mean, we can have a lot of that, and pretty much done. But does everyone understand what we're doing in that stuff? Then? We're basically saying that we're stealing the assignments. And once we steal the assignments, these are gonna be firmly won. Does that make sense, everyone? Anyone that's confused with this stuff, you guys all look pretty confused, I'm sorry. Yeah, so what we're done stealing. This is still not 0.85, this is still not one yet, right? So we're gonna look for the next closest unmarked point. Which one's the next closest unmarked point? Start graphing. First we go next. Let's look at that point, it's gonna be juicy, right? All right, we're going to steal it. We're like, alright now. So this is going to be equal to 0. So now over here. This will be 1. This is now going to be 1.15. Can we have yj equal to 1.15? No, so actually this value is 1. And what happens to that 0.15? It disappears. Cool. Our algorithm is like that. This is going to be equal to 1. That's it. The end. Okay, cool. So it's going to steal it. What's going to happen to this? Anyone tell me what's going to happen to this point? Yeah, this one's going to be assigned. And that's going to be 1 for the assignment, 1 for the assignment. This is going to go away because it's no longer. This is going to go away. Does that make sense?
When you take it away, you need to.
Yeah. Yes.
If yj was already 1, why did we assign that point to 1.2?
What do you mean by it's 1, 2, and 3? Oh, yeah, I see what you mean. So yj is different than x actually. So yj is just referring to that what you get. So, the moment that we declare this an actual vector, we're just gonna absorb everything. And because this can no longer be a vector, right? So all the points that used to consider this a vector are now going to be a vector. So I can, yes. Put it into it. Yeah.
So it happens to that point that was attached to.
Here, this way?
Yeah.
Oh, it's not in this. Yeah, kind of magic. Yeah, yeah.
So why is it that like for that xij, and I'm finding 0, and then that xij. 0. Like what, sorry, like the one above, and why is it that like xij can, like the eyes can be reused with the data sheet, like why is it not like x? I data, because in the xij case, you're talking about anything. Like some other point, but in the xij double time case, how can it be like the eyes? I guess it is.
Yeah, so I think it's this line. So for every point with x ij prime greater than 0. This is basically cycling through every single I that's been assigned j prime. That's the point. Does that make sense? Oh, Miranda?
Why do we have to, for all of j double equals to?
Yeah. Great question. Yeah, why do you have that? Oh, I think we're setting J double prime. So anything that has some function of them, this is bad notation. But basically we're saying this used to be J prime, it's now equal to J. So I guess it should be more than that. in terms of J.
So it's changing the value of y or
J. So this value, Xij, remember, so we're cycling through all the i's, and then we have this value, and this will be J prime. This will be value set to J, and every single X for each I is going to be assigned to J. So maybe it was assigned to J times 4, value times J. Liz? Yeah, so it's just that. So, what's the next couple of these then? So, we stole the center assignment here. So this will now be assigned to A, so B. But then what happens to E? That used to be, what happens to E? Because E used to be pointing to it. Well, it's gone. These are no longer pointing to E, because all of them are going to A, only A. Every other point that goes to D or E or B, these are going to go away. Bye-bye. Bye-bye. Make sense?
Wait, so then if we do something, if we say J double thing, then we say double.
I'm not too sure what's my option. You should go after. Yeah, sorry. Doesn't take it out of that. You get out later. But you understand what I'm saying with like review assignment. Awesome, yes. Okay, why don't we look at the approximation? So does anyone have any questions about this surrounding? Before we move on? Yeah,
the second, like the very last line,
yeah,
is it called?
it's called feature, I'm sorry. So basically, every single time we run this, we're gonna mark these, and that just tells us that they're no longer, like, we're no longer looking for them. So basically, when we do this, well, maybe this is the next YG that we choose. It's not gonna touch any of these points, because we've already marked them. Make sense? Yes, Ellen.
I guess like when we did the LP rounding for the other stuff, like when we found it, it still fell within like the constraints per se, but like when we do this, wouldn't it exceed the
That's a great question. Yes, yes. So, like Ellie said, the distance between this point and maybe this point, maybe it's not within R. Where do you think R is going to be? And so let's just draw a marker. It's gonna look something like. That's R. Is this within R? No, it's not. R from A. So how are we gonna do our approximation of this? Well, what's the distance between this point and this point? This point and this point. What, R, yeah. And what's the maximum distance between this point and this point? R, yeah. So these are both bounded by R. Does that make sense? Yes.
So this is max, this is between A and the other one are supposed to work it. Cause I thought like, they're different centers, so it's not like, well, wait, right now, that is part of our center, but.
Well, we saw before that, if we look over here, yeah, so basically the way that the LP want to place the points, the closest, I guess, so this would be within R, this would be within 2R. This would be within R, and then any other point that's not being assigned would be within 2R. Oh. Yeah, so this is, again, A and B are R, right? Because our LP will, assign A and B. And what does the LP do?
That will be required then, like, if you have it,
If you assign it there, brings it to R. The same goes with here. So the distance between, basically, this rounding algorithm guarantees a 2 approximation.
So then I guess, yeah, so my original question is, A, doesn't normally have that top one assigned, so why did you say that on? Cause like A gets assigned to get middle.
Yeah, that's a great question. I guess this would be, if you chose this as your center, right, in our normal case centers, if these are the closest unmarked points, then, it would want to choose one, two. So it would choose it in the original K centers, two. Because the algorithm should be aligned. Why not necessarily? Because, again, maybe the LP doesn't do a great job, and it, I guess, it's only has this like tiny little cluster. And maybe this one, something went well for this one, and it gave one to itself. Yeah, so this is still the option, I'm sorry, it's still the obvious. So just, know that the two approximations because this step, while y is less than one, is only going to move the closest to it, that would fall within the. Yeah. And so these points that are outside of this radius are within too far. Because of the same thing. But yeah, so this is a 2R approximation problem. What else? You can extend this problem into K medians, K medians, same principle. That's kind of nifty, isn't it? Yeah, any other questions for K medians? That's the end of the lecture. If anyone else has any questions, feel free to ask. But yeah,
Moving back to the original question that we had with the I and J prime, just so I'm understanding it correctly, if we weren't switching the I's and J's, would it be correct to say like X, J prime, and then J double prime for all J double prime that were in the J prime?
wait, you
X, J prime,
right?
J double prime for all J double prime that were assigned to J prime. I just what like,
Don't forget this is XIJ.
oh,
So are you doing it XJ times?
or like if we weren't switching around the I's and J's. Yeah, like, cause it's really, or it's a little bit confusing for me.
Yeah, I don't think that. Because you're saying. Because again, these are the I, you know, this is the J, assigning to this. So what do you mean that is the I? Well, in the XIJ, okay, wait. If this is pointing to here, we're not gonna be the J. I can make them down.
Okay. I get it, like, when you draw it, but I don't understand it with notation, so, yeah.
Okay, let's try and. I'll do it.
Why would it just be XIJ in one and XIJ?
Because this is J prime, this one is J. So this is some point, so XIJ, okay, let's look at this one, XIJ, XIJ prime, and XIJ double prime, right? So let's refer to one of these points as I. So this is I. Okay, this is I now. So XIJ originally, XIJ prime is the original. So this used to be assigned to this J prime. Okay, that's not gonna happen anymore. So now, XIJ is going to happen. We equal to one. So this was one, it's not even 0. But this was some value that's not one. Some value. No longer, it's not 0. So Xij here is going to be assigned to 4. Before it was assigned here, now it's going to be assigned here. And now for every single Xij double prime, this is some double prime. Maybe there's another point F that is also, prime. So for every single point that isn't J or J prime, it's going to cancel each other.
So what point can we assign?
Yeah, that's what the LP does. Yeah, don't forget the LP can assign a point to the center, then a darn job with the LP rounding out to assign it to one center and one center. Does that make sense? And it's one center that we choose. Okay, any other questions? All right, sounds good. Please give me a 5 stars on my record professor. Thank you for coming. That's it.
Thank you, Cheryl. Thank you.
I hope that wasn't speaking to you.